In the early 1970s, a Princeton physics professor named Gerard K. O'Neill asked himself a question that seems simple and produces an answer that is not. Is the surface of a planet the right place for an expanding technological civilization? The question sounds rhetorical, framed as it is in that slightly arch academic style. But O'Neill meant it literally, and he developed it into a systematic engineering analysis that produced one of the most detailed and influential blueprints for human civilization in space that has ever been seriously developed. His answer to the question was no. Planets, he argued, are resource-efficient places for the origin of technological species. They provide gravity, atmosphere, and a concentrated surface area during the long period when a species is developing the technology to leave them. But they are not necessarily the right form factor for a civilization that wants to expand significantly beyond the population and resource limits of a single world. And the alternative he proposed, free-floating, self-contained habitat structures at specific stable points in the Earth-Moon gravitational system, is what we now call the O'Neill cylinder. The fundamental physics of the O'Neill cylinder starts with a problem that every concept for permanent human habitation in space must solve: gravity. Human physiology evolved for Earth normal gravity, approximately 9.8 meters per second squared at the surface. Extended exposure to microgravity, as documented by research on the International Space Station, causes significant physiological deterioration, bone density loss, muscle atrophy, cardiovascular changes, fluid redistribution, and vision impairment from intracranial pressure changes. For short missions, these effects are manageable and largely reversible. For permanent habitation, they would be disqualifying without countermeasures. The only practical method for generating artificial gravity without an actual planetary mass is rotation. A rotating structure experiences centrifugal force that acts, from the perspective of objects inside, exactly like gravity, pushing outward from the axis of rotation. The perceived gravity on the inner surface of a rotating cylinder is proportional to the radius of the cylinder and the square of the angular velocity. O'Neill's specific cylinder design, the Island 3 configuration that became his canonical proposal, specified cylinders approximately 8 kilometers in diameter and 32 kilometers in length, rotating at approximately 2 rotations per minute to produce Earth normal gravity at the inner surface. Each cylinder would house approximately 10 million people. The habitat would be located at the gravitationally stable Lagrange points in the Earth-Moon system, specifically at the points designated L4 and L5, which are positioned in the Moon's orbit around Earth, 60 degrees ahead of and behind the Moon respectively, and which are stable equilibrium positions where a structure can maintain its position indefinitely without active propulsion. These points have subsequently given their name to the L5 Society, a space advocacy organization that was prominent in the late 1970s and early 1980s. The interior of an O'Neill cylinder would be, by design, a self-contained biosphere. The inner surface of the cylinder, the surface where inhabitants would live under the artificial gravity of rotation, would be divided into alternating strips of habitable land and transparent window panels. The windows would admit sunlight, which would be redirected into the habitat by external mirrors. The day-night cycle would be simulated by adjusting the angle of the mirrors. The habitable strips would contain agriculture, forests, lakes, rivers, residential and urban areas, a miniaturized Earth environment designed to support millions of people indefinitely. The closed-loop ecology that O'Neill envisioned, in which waste is recycled into soil nutrients, water is purified and recirculated, atmosphere is maintained by plant photosynthesis, and food is grown within the habitat, draws on the same principles as modern closed-loop life support research, and faces the same fundamental challenge. Biological systems are complex and not perfectly controllable, and maintaining a stable, functional biosphere in a sealed environment is an engineering problem that has not yet been solved at scale. Biosphere 2, the experimental closed ecological system built in Arizona in the late 1980s and early 1990s, attempted a version of this challenge at a small scale and encountered significant difficulties maintaining stable oxygen levels and species balance. The designers of a full-scale O'Neill cylinder would need to solve problems of ecological engineering that Biosphere 2 illustrated but did not resolve. The materials and energy requirements for building an O'Neill cylinder at the scale O'Neill envisioned are large, but O'Neill's analysis argued that they were not beyond reach given the resources available in the solar system. The key insight was that the material for the cylinders should not be lifted from Earth, whose deep gravity well makes every kilogram expensive to launch, but should instead be sourced from the Moon, which is a gravitational well roughly 6 times shallower, and from the asteroid belt, which contains raw materials in quantities that make Earth's entire mineral endowment look modest. O'Neill proposed a mass driver, essentially an electromagnetic railgun built on the lunar surface, that could launch lunar regolith into space at the velocities required to reach L4 and L5, where it would be processed into structural materials. This proposal, extracting materials from the Moon and using them to build habitats in space, while solar power collected in orbit provided essentially unlimited energy for the industrial processes involved, was the foundation of an economic model in which space settlement became self-sustaining and self-expanding. Each habitat, once built, could produce the resources needed to build more habitats. The exponential logic, if realized, implied that the long-term carrying capacity for human civilization in the inner solar system was vastly larger than any planetary surface could provide. O'Neill calculated that the interior surface area of habitats that could be built from the material available in the asteroid belt alone, even a small fraction of it, exceeded the surface area of Earth by orders of magnitude. The O'Neill vision fell out of mainstream consideration in the 1980s as the Space Shuttle program consumed NASA's budget and political attention, as the economic boom of that decade reduced urgency about resource limits, and as the technical challenges of even the much more modest space station program became apparent. It has returned to serious discussion in the 21st century, driven by 3 developments. First, the dramatic reduction in the cost of reaching orbit through reusable launch vehicles. The economics of space access that O'Neill assumed have improved substantially since his original analysis and continue to improve. Second, the renewed interest in space resources, asteroid mining, lunar resource extraction, that has produced both commercial ventures and government programs. Third, the explicit endorsement of O'Neill-style free space habitats as a preferred long-term model by prominent figures in the contemporary space industry, most notably Jeff Bezos, whose Blue Origin space company has described O'Neill cylinders as the preferred destination for heavy industry moved off Earth. The case Bezos and others make is distinct from O'Neill's original framing, but compatible with it. Heavy industry, manufacturing, resource extraction, energy-intensive production, currently conducted on Earth's surface, causes environmental damage. Moving this industry to space, where solar energy is unlimited and there is no biosphere to damage, would allow Earth to recover toward something more like a nature preserve while industrial civilization continues and expands in the space environment. Whether O'Neill cylinders are built in the 21st century, the 22nd, or not at all depends on a sequence of technical, economic, and political developments that cannot be predicted with confidence. What O'Neill established, with the rigor of a physicist rather than the enthusiasm of a speculative writer, was that there is no fundamental physics barrier to building them. The materials exist. The energy exists. The orbital mechanics are understood. The challenge is engineering at a scale humanity has not yet attempted, and an economic model that makes the initial investment rational, which requires either dramatically lower space access costs or dramatically higher perceived value from space-based resources. The cylinders O'Neill imagined would look, from the outside, like enormous aluminum cans tumbling slowly in space. Inside, they would look like the Earth, scaled down, fields and forests and cities under an artificial sky. 10 million people per cylinder, under the steady, fake gravity of rotation, in an ecosystem closed against the vacuum. He asked whether a planetary surface was the right place for an expanding civilization. His answer was a blueprint. Whether we build, it is up to the civilizations that follow.